Hi everyone, my name is Sarah Tan and I'll be the moderator for today's talk. We're really excited to have with us Lizzie, Kumar and Amirata Ghorbani in our first ever seminar for 2021. This is this is also our first Rising Star seminar series of 2021 as well. So to tell you a bit about the format, this first hour is recorded and live streamed to YouTube. If you don't want to appear in the recording, please exit Zoom and watch YouTube, but come back again later. And the second hour is not going to be recorded or live streamed. Oh. So just to very briefly introduce the Trustworthy ML Initiative, we started out late last year as a group of people interested in this area of research. And now today we have various efforts, including this seminar series, resources. We want to provide a platform for early career researchers to showcase your work. We have an active Twitter, and in particular this year in 2021, we're going to be making a symposium. So encourage everyone to stay tuned for that. So for today's agenda, for the first half an hour, we will have Lizzie Kumar giving her talk and 5 to 10 minute Q&A. And this at 12:30 p.m. We'll move to Amirata Ghorbani giving his talk, and then Q&A at the end. We have a 5-minute break, and then we'll have participant-driven discussion. We encourage everyone in the audience to submit, upvote, and comment on any questions throughout the entire first hour using the Zoom Q&A tool. And I will be calling on people to present their questions. Okay, so we have, we're really excited here today to have these two awesome speakers. Lizzie is a second-year PhD student from the University of Utah. And Lizzie's talk is going to be epistemic values in feature importance methods, lessons from feminist epistemology. And Amirata is going to talk about equitable valuation of data. And Amirata is a 5th-year PhD student at Stanford. So two really awesome Rising Star speakers. So we're going to start off with Lizzie. So Lizzie, please take it away.
Great. Okay, can we see the screen okay?
Yeah.
Great, awesome. Well, thank you so much for having me here at this very generously titled seminar series. I'm really excited to be here today talking about a new paper to be published at FACT this year with Leif Hancox-Lee called Epistemic Values and Feature Importance Methods, Lessons from Feminist Epistemology. So today I will introduce the idea of feature importance and epistemic values and explain the inquiry we conduct in our paper. I'll talk about some of the epistemic values we find embedded in feature importance methods, including instrumentalism, universalism, and emphasizing abstraction over context. Finally, I'll offer suggestions for explainable ML researchers that draw from feminist ideas, incorporating subjugated points of view, evaluating explanations in context, interactivity, and seamfulness. As I'm sure you all know, machine learning has become an incredibly common method for building automated decision-making tools in research and industry. Once these models are built, it's up to humans to decide whether they trust that model to actually make decisions, and after deployment, to navigate a world in which that model is actually making decisions. As state-of-the-art models become more complicated, people are increasingly worried about being able to interpret them so that they can do those things effectively. One of the oldest and most common strategies in the growing field of explainable machine learning is simply trying to quantify the relative effects of each of the model's input features. This is something that was a part of my workflow when I worked as a data scientist, and it was something that stakeholders asked about and engaged with a lot. On this slide, I've included an excerpt from an ethnographic study of a data science team where a familiar interaction takes place. Some data scientists build a predictive model to automate a marketing task. In this case, it's churn prediction, or the detection of currently active customers who are likely to cancel paid services in the future. Then they try to describe the model by measuring the important features, and the stakeholders will use that to make some sort of judgment about the model. In this case, the stakeholders were encouraged, not just by the model's accuracy, but that it had identified features they expected to be important. As for features that were marked as important, but weren't expected to be, they had to decide whether to take it on faith that the algorithm figured out something new, or use this as evidence for skepticism about the model. So understanding the way we calculate feature importance has implications for the human process of machine learning model development. For our purposes, feature importance is any way of assigning quantitative importance to the input features of some learned function for the purposes of interpreting or explaining that function. Some tools you might have heard of include local or instance-specific metrics, which try to explain the model's output on a certain input. Some commonly cited ones include LIME, SHAP, gradients and integrated gradients, and counterfactual and explanations can also be interpreted this way. Another family are global metrics, such as permutation feature importance and Gini importance for tree ensembles. Saliency maps are also part of this category, where the features are individual pixels of an image. So why am I talking about epistemic values in the context of feature importance? Well, epistemology is the philosophical study of human knowledge, and key to any conception of what constitutes a useful interpretation are epistemic values, or desirable qualities of knowledge and understanding within a certain theory of epistemology. And while many feature importance methods are defined and justified in formal or mathematical terms that seem objective, the choices that were made in deciding how to develop or use that tool implicitly embed values. The lens through which we chose to write this paper was feminist epistemology, which grew out of a reaction against scientific claims of unitary knowledge, where largely white and male knowers have constructed one way of seeing as the objective one. I've included two of my favorite quotes from Donna Haraway, one of many voices in this movement that I think describe the version of feminist epistemology that we're interested in. Feminist objectivity is about limited location and situated knowledge, not about transcendence and splitting of subject and object. Relativism and totalization are both God tricks, promising vision from everywhere and nowhere, equally and fully, common myths and rhetoric surrounding science. So here are some examples of things that are valued in feminist epistemology. And not every thinker in this field would agree with every point here, but they're generally thought of as being under this umbrella. One is pluralism, which is the idea that knowledge is situated or contextual. And there are many locally correct truths from different perspectives, which together form a more complete truth. Another is standpoint theory, or the idea that marginalized individuals are better suited to provide objective accounts of the world because of their unique social position. Another is interactivity, which is the idea that objects of knowledge are not just passive with static properties, but should be considered as agents that can enter in conversation with the knower. These phrases may sound familiar if your interests in data and feminism brought you to this talk, because this amazing book, Data Feminism, came out last year, promoting these values in the practice of data analysis in general. These ideas have also influenced lots of the interdisciplinary work I've seen come out of the FACT conference in the last year or so. And keeping these values in mind while thinking about machine learning explanations led Leif and I to write this paper by asking the following questions. What are the epistemic values implicit in feature importance methodologies? Are these values in conflict with feminist epistemology? If so, can these conflicts help us understand the suitability of feature importance for explanation purposes? And finally, how could we approach explainability to be more aligned with feminist thought? So let's talk about the first question. What are the epistemic values at play when feature importance techniques are proposed? Some descriptions of the idea of feature importance mirror this one from the popular book, The Elements of Statistical Learning. Often, only a few of the features you fed into your model have substantial influence on the response, and are irrelevant and could just as well not have been included. Measuring the importance of a feature to determine whether it should be used in a model of a data generating process is actually an old statistical idea, but using it for interpreting a black box model is a relatively new idea. In particular, the idea of assigning importance based on predictive performance versus some other statistical notion of model fit was really not a concern until people started being able to extract predictive insights from uninterpretable functions of huge variable sets due to advances in computing. Matthew Jones at Columbia argues that Leo Breiman, who developed the idea of decision tree ensembles, had his perspective on modeling drastically shift when he worked in the defense industry. Leo Breiman proposed a new influential view of data analysis, which de-emphasized the importance of developing probabilistic models of underlying data generating processes. He argued that a prediction-centered view was the right way to investigate the relationship between response and predictor variables, and that black box algorithmic models provide more reliable and interesting information than weakly predictive data models can. He also pitched one of the first so-called feature importance techniques, which was based on the change in a random forest model's accuracy on out-of-bag samples when the feature of interest is scrambled. Even though his personal view was that variables were only important if their deletion impacted accuracy, his goal when he calculated these importances was not to simplify or prune high-dimensional models at all if it wasn't necessary, as he believed that the advantage of using trees and ensembles of trees was exactly that it allowed one to avoid doing feature selection. His goal was instead to appease those who had interpretability concerns, which he wrote was a secondary goal that could be finessed. And so we argue that this form of feature importance was born from the value of instrumentalism, the view that the value of a theory is determined by the extent to which it helps to make accurate predictions, and not by an absolute or literal notion of truth. And while some have taken a stance on whether or not this aligns with feminist theories, our point is that this choice is not neutral, which has also been pointed out in other contexts. Something that we have been seeing a lot of in the explainable ML literature recently is the method of stating some desirable quantitative properties up front and then trying to derive explanation methods which satisfy them. And this has seemed to be a very convincing argument for many people because these methods are popular and keep getting used or built upon, especially Shapley values. If you're not familiar, the Shapley value is an idea from game theory that allocates the value of a coalitional game among players in accordance with these three axioms. The idea behind Shapley value explanations is that a prediction from a model can be interpreted as a game, and the features can be interpreted as players. And thus the allocation of the prediction among the features become their importance. The appeal of Shapley values is that once you impose all three axioms, there is a unique solution to the allocation problem. But we want to examine the idea that explanation design should be done this way. While it's good to be able to say something definitive about the behavior of mathematical tools, the fact that this methodology is valued in our field may tempt researchers to impose axioms for the sake of imposing axioms in order to arrive at a unique solution. I really like to highlight this excerpt about the third Shapley value axiom, additivity, from a game theory textbook, which casts doubt on why it is included at all. The authors of this book call it mathematically convenient but hard to motivate, and this criticism has existed for decades. The cautionary point that we're making here, which is not to assume that some kind of nice mathematical property will result in useful explanations, has been made by other authors in the last couple of years, which have supported their points with user studies. Even though this is not a novel criticism, we can connect this exact point back to our feminist lens. The temptation to show that there is a universal or unifying solution to the problem of explanation, which I've called universalism here, is in tension with the value of pluralism, which is a point that has been made in the context of HCI and design because different qualities may be desirable in different settings and by different individuals. Another value we sometimes see in the feature importance literature is the tendency to try to explain a model in a vacuum rather than in a real life context when it's operating on real data. One example of this value in action, which I'm sure many of us are guilty of, is attempting to empirically demonstrate the success of some method in a contrived manner that doesn't reflect the reality of how it will actually be used and to what end. And a valid response is to say, oh, if we had more time or resources, of course we would do that. But it's still a choice that papers without studies of this type still get submitted and published. Another example is the proposal of axioms such as input invariance, which posit that explanations should be robust to transformations of the training data. Finally, many feature importances are calculated by running potentially unrealistic inputs or out of distribution samples through a model. This includes SHAP, or at least the most popular version of it, as well as other permute and predict methods such as permutation feature importance and counterfactual explanations. Some of these properties can lead to issues which again have been pointed out by other researchers. In the setting of recourse, when a model has made a decision about a user that they want to change, such as their credit application being denied, feature importance explanations that show them how to navigate to the model's decision boundary may appear to be helpful, as they can show an individual which features they might have to prioritize changing, such as their income, to be approved. In reality, though, there are assumptions about the user that you have to make for that kind of explanation to be informative. In particular, there may not be actions, the user can take that map to a change in the value of some feature. Additionally, being able to provide the most useful possible explanation for a user would require incredibly detailed information about that user, resulting in a tension between usefulness and privacy. As for the out-of-distribution problem, there is some evidence of undesirable consequences that come from evaluating models on out-of-distribution samples, including vulnerability to adversarial attacks and bias towards extrapolation behavior. We can connect this back to feminism by saying that social context matters and that we should consider the data we operate our model on as part of a larger socio-technical problem setting. Before I move on, do I have any clarifying questions?
No, none so far. So, I recommend just, finish your talk and then we can do more questions later. Yeah.
Okay. All right, so I will mention some of the alternative ways to approach explanation from a feminist perspective. One suggestion is to incorporate subjugated points of view when designing tools for understanding systems. Since knowers are not interchangeable, those affected by algorithmic systems know better than ML researchers about what kinds of tools will help them understand those systems. An example of designing transparency tools based on this theory was presented by Mike Cattell at FACT last year, where participatory methods, or a design process which includes the participation of a certain community, were used to develop an algorithmic accountability toolkit. And I'll note that this idea has been explored in the broader context of machine learning in the participatory ML workshop at ICML last year and beyond. Another suggestion, which is maybe an obvious one, is to evaluate explanations in context. In evaluating explanations in a feminist spirit, we should consider various contextual factors that affect how well an explanation can perform its social function, such as how explanations are interpreted by stakeholders, unintended consequences, how explanations perform in realistic applications as opposed to toy datasets or problems, and what context exists that could cause an explanation method to fail. HCI research suggests that there might be more interactive ways of creating explanations. One example is Gamut, a visual analytics system that provides an interactive interface to support the interpretation of generalized additive models. Another idea that reflects a pluralistic perspective would be to seamfully design explanations. Seamless designs are meant to make the usage of a tool natural and invisible, whereas seam-full designs make the seam between tool and user highly visible. Seamful explanations would encourage users to avoid over-trusting one interpretation and keep multiple interpretations in mind. Some concrete ways explanation researchers could do this is purposefully blocking the most obvious interpretations of explanations if they are misleading. For example, we could design feature importance bar charts in a way that reminds users that features may be related or correlated instead of discrete and separate. Or we could illustrate that explanations are not causal when they do not represent causal quantities. We could work on ways to communicate uncertainty and downplay the authority of an explanation, which is an idea that has received lots of attention in the data visualization community. Finally, we could design explanations in a way that is ambiguous and thwarts any one interpretation, providing multiple plausible accounts of the same phenomenon. So returning to our key questions, we find that looking at the epistemic values implicit in feature importance through a feminist lens can highlight potential weaknesses or failure points of existing literature and offer directions for the field of explainable AI built on feminist thought. Thank you.
Thank you, Lizzie, for the really interesting talk. And just as a reminder to audience, please use the Zoom Q&A to ask any questions. We have a question from Chirag. Chirag, can you ask your question?
Yeah, sure. Hi, Lizzie. So I think one interesting aspect of this work would be that you mentioned about pluralistic explanations, right? So we can always come up with different versions of explanations for different end users, right? So, and one can actually prefer one explanation over the other. But then the follow-up question would be, how well attuned are all those individual explanations to the model? Like for example, I can for me, the red color would be an indication towards an image of an apple, or for someone it would be like this, just the shape of it. So how do we evaluate that in that case?
Evaluate what exactly?
Like different versions of explanations, because like one of the ways to evaluate explanation is using human study, right? Mm-hmm. But then again, if I'm providing 5 different explanations using a pluralistic approach, then maybe 5 different people would be preferring 5 different explanations.
Yeah, that's true. And I think maybe a pluralistic response to that would be, that's okay. And you don't need to find the best explanation between those 5. Or, you know, one thing that I haven't really seen done much in this literature is doing more sort of case study based evaluations of explanations versus user studies that try to quantify what like kind of the best way to do something is. Right. So trying to get sort of a descriptive, qualitative understanding of what people, how people process those explanations. I don't know, Leif, do you have any other responses? Leif is here, by the way. Hi.
Hi, Leif.
Hi, yeah. So I guess like to add on to that, I guess like when you have 5 different explanations, it doesn't mean that they're all equally good. I think then you need to dig more into the reasons for why people take those explanations. And I think that's something that's lacking in like mechanical Turk studies when you know a lot of explanation research just does a very large scale mechanical Turk study and they ask people to take explanations based on that, but then they aren't able to do the qualitative work to figure out like what is the context in which people decide this explanation is better than the other.
Mm-hmm. Right. Makes sense. Thank you.
And we have our next question coming from Kaveh. Kaveh, can you ask your question? If you hear me, if you're online.
Hi. Thank you, Amirata. I want to know how we can validate that a subset of feature is performing good for a problem.
Maybe Kaveh, can you elaborate a little bit more?
You know, for my problem, I have 30 features. I did some experiment, and I think 5 out of 30 is enough for my problem. How I can validate it? I should compare the accuracy to the whole set when we have all the features. Is there, could you give me any clue how to do that?
I mean, I guess the first thing I would ask you is, what is your goal? Like, do you want the most accurate possible model, or is your goal to have a very compact model? Does it need to be interpretable? I definitely don't have an objective answer to that question, or a single answer to that question.
Yeah. Thank you.
But also maybe continuing more along that lines, talking about pluralism, maybe there is not like one, the act of saying that, oh, I want to pick 5 features that are important out of the 30 that I have, is already going towards a universalism kind of axiom. So maybe I would suggest maybe also thinking about the context of like, why do we say that we need to have this 5, and like, is it this 5 for like everyone, or stuff like that as well. Yeah. Lizzie, I really appreciated Lizzie and Liv, I really appreciated how your work, it was really interesting to see the primary source of like Leo Breiman saying this is what he was thinking when he created the permutation feature importance way back then. I wanted to maybe go a bit towards like what should a data scientist do in this context? Shapley values is obviously one of the hot feature importance methods right now, and you have pointed out like some of some questions about the additivity axiom as well. A data scientist comes into the room, looks around, sees a bunch of feature importance methods. Shapley values is one of the popular ones right now. What kind of things should we keep in mind when we're like deciding whether to use this or not? And yeah.
Leif, do you want to take a stab at this?
Yeah, sure. I guess like I'll target the small machine learning researchers and stuff, because I guess that as a working data scientist, there are restrictions, right? You have a limited time to do a project, and so even if the existing tools are not ideal, according to what we argue, then you don't have the time to go create your own tool necessarily. So I guess a compromise would be like, it would be nice. Like I find that a lot of data scientists, like, or at least in my organization, have kind of a kind of in their own like silo in terms of what they think of as best practices. And so like just exposing yourself to more different practices would be a way of getting more perspectives, rather than just sticking to tools, But of course, I do, with the caveat that again, we understand that the data scientists have time limitations on terms of projects, and you don't necessarily have the time to explore more things. But I think in general, that's a good thing if we are given the time to explore more things, and also other things like working with, if your organization has the resources and you can actually work with social scientists to like, study like what are the best tools to use and what works best for your team. Like getting more into this new perspectives would be good. But again, this is all resource limited.
So then advice towards a budding machine learning researcher who is, thinking about coming out with the next greatest feature importance method, like what might you want to say to them then? Because this is someone who's actually like trying to design some new methods.
Right. I mean, I guess in that case, I mean, a lot of the suggestions we had in the paper, which we promise we will post a preprint soon once we have done our revisions. But would just be that I think there's to think more about the qualitative research you can do, because just quantitatively measuring stuff on Mechanical Turk is a very limited perspective on the effectiveness of explanation. So I just encourage more qualitative research and like working with UX people or social scientists to like figure out the social function, whether like the explanation is achieving its social function, not just a mathematical function.
I think a question that people don't ask themselves enough is also why they think feature importance is going to solve their problem. Like, I know that's sort of what explanation can be shorthand for right now when we talk about local explanation? I mean, I know there's a variety of what counts as an explanation in machine learning right now. And I guess if your first instinct is to go for a feature importance method, my first question is why? And what does that have to do with your use case or what you're trying to find out?
Cool. Great discussion. And so thank you so much, Lizzie and Leaf, for the talk and discussion. And now I'm going to cue in Amirata, who's the speaker for the second half hour. So yeah, Amirata, please take it away.
Hello, everyone. So Sarah, do you hear me?
Yeah, we hear you.
Awesome. So today I'm going to talk about a method for equitable valuation of data. We'll jump right into it. So let's have a motivating example to begin with. Let's say you have an AI for health company, and your job is to detect melanoma. And your model with the data set you have has around 60% prediction accuracy. So what you naturally do is that you do all your best to train the best model, but then you think like you need more data. So you go to a hospital, buy some new data, and your model's performance increases. But the question is how much you should pay to that hospital. Like how much of the 80% melanoma prediction credit should go to the hospital, or how much of it should go to the original data you had. And data valuation matters for everyone who's dealing with data. So if we're talking about machine learning engineers, researchers, we're usually working with heterogeneous sources of data. So we want to know what's the quality of each of them. If you're a data vendor, your job is to value data because you're buying and selling data. But if you're an individual sitting in your home, you basically need to know the value of your data because companies are using your data without your consent. And there are laws being created right now that force companies like Facebook to pay people their data dividend. So to value data, we go back to the very individual elements of machine learning. So any machine learning problem, at least in the supervised setting, can be divided into three different pillars, basically. So you have your training data, then you apply a learning algorithm to it. So we look at the learning algorithm as a black box. So it can be training a linear regression, tuning the hyperparameter, blah, blah, blah. It's just a black box that takes in the training data and outputs a predicting model. And once you have your trained model, you have a performance evaluation metric. So it can be test accuracy, F1 score, or even the revenue your model generates when it trades in the market. And the goal of finding the data value is to kind of divide that model's performance, that model's value, among its individual data points or sources of data. So both of them, I'm going to use them interchangeably. And here, for instance, your model has a performance of 0.8, and you divide it and you see like Pentagon data set gets 0.4, but star data set or data point is not as good, so it gets 0.05. So the value depends on the problem, on your learning algorithm, and also the evaluation metric you're using. And if you think about it, there are infinite many ways to divide the performance of the model among its sources of data. So what's the right way? So there's a Lee-Van score, which is a very famous concept in statistics. So let's say we're looking for data point stars value. So I train a model on all of the data sets I have, and I get 0.8 performance. Now I throw out data point star and train a new model, and I see the performance drops by 3%. So the Lee-Van score, Lee-Van method of evaluation will get 3% value to data point star. But is it a reasonable way of valuing data? And to answer that, we need to first define what we mean by reasonable. So what are the desirable properties of evaluation method? So I'm going to talk about three very basic properties that intuitively should be satisfied. So one of them is a null element property, which means that if there is a data point or a source of data that is useless in the most comprehensive way of thinking about it. And the way we define most comprehensive is that if I add this data point to any subset of the training data, it's not going to add any value. It's not going to add any change in the performance. That should get 0 value. The other feature, which is more of an equitability feature, more of a fairness feature, is symmetry. So if I have two data points that are in the most comprehensive sense interchangeable, in the sense that if I add either of them to any subset of the data, the change in performance would be the same. They should get equal value. And then linearity. So let's say I have a bunch of ways to evaluate my model. So let's say it's accuracy, latency, F1 score, fairness. And my final metric is a linear combination of all these metrics. I want the value to follow this linearity. So the most basic linear metric you have is basically test accuracy, because it's the summation of individual accuracies on individual test data points. So these are basically Shapley axioms rephrased for the case of our problem. So it gets proved that the only value that uniquely satisfies all these drug properties is the data Shapley value. And this is how it gets defined. So before the formula scares us, let's delve into it and kind of understand it more. So I have a data point Z in a data set S, and I want to find the value of Z. So first assume S, in a data set D. So first assume S is any subset of a training data set. So you have 10 different training data points. Let's say it's 3 randomly chosen data points. I first train a model on S and look at its performance, let's say test accuracy. Then I add Z to S and train a new model. So this would basically be the leave-one out score of Z with respect to subset S. Then I normalize this performance, this marginal performance, with the number of possible subsets of that size. So if the data set is size 10, if we remove C, we have 9 data points. And if the size of S is 3, it would be 9 choose 3. And then we sum this over all possible subsets of data. So basically, data Shapley values is a weighted average of the leave-one out score with respect to every possible size of data. So instead of being focused on only the largest possible size, which is the leave-one out score, we're looking at how much performance change Z adds on average for every possible size of the data. So how much it adds to subsets of size 1, plus how much it adds to subsets of size 2, etc. So let's look at our simple example, and we want to find the value of data point star. So what are the subsets of size 2? It's hexagon and pentagon. So we remove data point star, and we see that the performance drops by 0.3. There are 2 subsets of size 1, so either hexagon or pentagon. So we add data point star to each of these subsets and look at the marginal performance. And there's one subset of size 0, and when we add S to it, we see the performance doesn't change. So the summation would basically be the data Shapley value of data point star. So this formula is exponentially difficult and computationally expensive, so we cannot compute it in practice. What we do in our work is that we develop efficient Monte Carlo-based algorithms to estimate this value. And this is basically the Shapley value that we were also introduced in the previous talk, but Shapley developed it. So it's in the cooperative game setting where you have a bunch of players, and when they collaborate with each other, they get some sort of reward. And for every subset of those collaboration, you can also find the reward they would have gotten if they collaborated. And in our case, we basically have data points or data sources as our players. So as we discussed, data points value is its kind of a weighted average of its contribution to performance. So what's a high value data? Let's go back to the formula we had. Let's say data point Z is high value. What it means is that usually when I add Z to any random subset of the data, it's improving performance. So it's a good data point. But it means if Z has low value, it means that if I add Z to any subset of the data, on average, it's going to hurt the performance. So it's a bad data point. So let's use this intuition and see what applications we can find. The most intuitive one is finding low quality data. So let's say I have a spam classification data set. And what I do is that in my training data, I just flip the label for 20% of data points. So I make their label wrong. And now my task is to go and correct the data set. So I have a data set with label noise and I want to correct it. So if I just randomly shuffle through the data and correct the wrong labels, I have to go through all the data points to find all the mistakes. But if I use data Shapley, and the way I use it is this, I sort my data points based on their value and start from the least valuable data point and start investigating from there. So what happens is that I have 20% of my data points mislabeled. And when I look at the 20% of the least valuable data points, I'll find most of the mislabeled examples and correct them. And it makes sense because if you go back to the definition of data sharply, it kind of corresponds to how much value data points add, and the mislabeled data point which will usually hurt your performance. And you can see leave one out score is not acting very well. But you can do the other way around, so you can find the most important data points. So for this one, you've worked with the UK biobank data set, so it has 500,000 individuals in the UK, lots and lots of health information about them. They're from 22 centers in the UK. What we do is that we create binary data sets for disease prediction. So let's say our task is predicting breast cancer, if someone's going to get breast cancer from their clinical data. So when we train a model on this, you're going to get around 68% test accuracy. And then what you do is that you start removing data points and you train a new model. And what do we expect? We expect the performance to drop because you're just making your training data set smaller. But the drop is pretty steady and slow. But what happens if we rank data points based on their data Shapley value and start removing points with the highest value? So here, I start removing points with the highest value and train a new model each time. As you can see, the performance drops very heavily. And just to make sure we're on the correct side, so there are three sets here. There's a training set that we compute the data Shapley value for. There's basically a first test set that we use to compute the data Shapley value. And there is this held out test set that we report these results on so that there is no overfitting going on. So as you can see, data Shapley is detecting the data points that have the highest value, and they're actually crucial for the prediction task. So here I have the majority of my training set left, around 60% of the points. But you can see the performance is already around random, meaning that although adding new data points will improve performance, but what actually is interesting is that there are a bunch of pivot data points, a bunch of very important data points that just should be there. And we can do this the other way around. So I rank data points from the lowest to the highest, from the most negative to the most positive, and I start removing them. And you can see here, after removing around 40% of the data points with the lowest value, the performance of the model actually increases. So it's kind of against the intuition that more data is always better. Here you have more data, but your performance is worse because you're having sources of data that are just not contributing positively to your task. And it doesn't necessarily mean that those sources of data are mislabeled or noisy or anything. It's just that for the classifier you are using, they're not contributing any value. So since the time the paper was published in 2019, people have used it more and more in different applications. So I just saw this paper from ACL 2020, where they used this for an NLP task, and they did the same thing. So they computed the data Shapley values for the points, and they removed the ones with low value. And without adding any new data or without using any specific training tricks or model tricks, they got state-of-the-art results with quite a bit of margin from previous best results by just removing bad data points. So this is not a work that was done by me. Now the last application, it's basically domain adaptation. So why domain adaptation? So let's say you have a training. So what's the setting of domain adaptation? In this setting, you have a training data, but your performance metric, let's say your test accuracy, is in a data set that is a bit different. So there's a bit of a data shift from training to test. So let's say your training data is driving in the daylight, but your test data is driving at night. So if you train a model on the first one, it's not going to be necessarily good on the second. But does anything change for our setting? So for the data Shapley setting, no, because if you go back to the definition, there are not many requirements. So you don't need the train and test distribution to be the same. You don't even need IID assumptions on your training data points. So you just have a black box that takes your training data and outputs a model. So it doesn't even need to be a gradient-based training method. And you just have a performance metric that takes in a model and reports a performance. So here, the only thing that has changed is that our performance metric is using a different data set. So how we can use data Shapley? We use the very, very basic intuitive algorithm, might not be the best. So you compute the data Shapley values of your training data points. with respect to your metric, which is accuracy on a different data set. And you remove data points with negative values, the ones that are just hurting. And for the data points with positive value, you reweight the data points with the relative weight, meaning that if a data point gets very high value, it's a very helpful data point. So you assign a high weight to it. And then what you do is that you do a weighted empirical risk minimization, a weighted training. So let's see how it works in practice. So there is this HAM 10,000 data set, and this data set is 10,000 clinical images of skin lesions taken by a dermatoscope, which is a device dermatologists can use to take high accuracy, standard lighting images of skin lesions. So you can assume it's a very expensive data set because it's both taken by a dermatologist with a device and labeled by dermatologists. So what I did is that I just sat down and searched every disease's name. So there are 7 diseases in the data set with different keywords on Google, and created my own noisy data set in 4 hours without having any specific expertise in dermatology. So this data set was created in 3 or 4 hours, with just searching in Google image search. And as you can see, there are some good images in it, but most of them are pretty noisy. So what happens when I train a model on this data set and test it on a chain 10,000, on the 7-class prediction task, I get around 30% accuracy. But now I apply my Shapley method. So I compute the data Shapley value of the points here. I filter them by removing the negative ones and reweight the positive ones with their relative value. So these are the highest value data points. And as you can see, they are pretty related to our target domain. But at the same time, the performance increases rather strongly. And again, just to make sure we're not doing any overfitting, there are 3 sets here. So there's a training data set, there's part of HAM data set that is used for data evaluation, and there is this separate held out HAM 10,000 that I report these results for. Another case is fairness, which is a very important one. So it's well known that existing models can be unfair towards the specific subgroups. So there's this LFW plus A data set. It's heavily male and heavily white. And there's this PPB data set created by Joy and Timnit, which has equal representation of every subgroup of skin color and gender. So equal number of white males, white females, black males, black females, and different grades of skin color. So it's a quite a fair data set, but very small. So it can be used for evaluation, but not necessarily for training. So what happens when you train a model? As you can expect, when you train a model in LFW plus A, its performance on itself is around 98%, but on PPB is around 84%. Why? Because when you look at its performance on, let's say, black females, the test accuracy is around 50%, so it's pretty bad. So we use, again, our adaptation algorithm. We compute the data Shapley value of points here versus performance on here. So now we have shown the highest value data points. So as you can see, they are all male. They're all female. And the performance increases, meaning that the model has become more fair because the data set has become more fair. Now, there is a problem with data Shapley value, which is, first of all, it's very detached from machine learning and statistics because it's just a game theoretical setting applied to a machine learning problem. And secondly, it has no distributional assumptions. Usually training data is coming from a training distribution. So in a completing work, we introduced the distributional Shapley value, which this time, instead of having a fixed data set, you have a training data distribution. So you don't just have a data set of fixed points and you're computing the values for them. You're given a training data distribution and you're computing the value of a query point with regards to that distribution. And there were lots of kind of statistical consequences following this assumption that we don't have the time to talk about here, and you can refer to the original work for that. But just the definition is quite intuitive. So let's say I want to find the value of data point Z versus this distribution D, assuming I have n points, I have a data set of size n. So what we do is that we just sample n points from data set D, from data distribution D, to get data set Z, so to get data set B. So data set B is just a random realization of a training data set of size n-1. And then I compute the data Shapley value of Z versus this data set that has Z in it. So it's kind of a random variable, which is the data Shapley random variable. So instead of having a fixed kind of deterministic data Shapley value, that the data Shapley value itself becomes a random variable because your training set is not fixed anymore. It's just a realization of the training data distribution. And if we take the expectation of that over our distribution, that will become the distributional Shapley value of C. So there is one problem with data Shapley values fixed because there's no fixed dependence on a specific data set. There's a different way of kind of showing this formula or equivalent form, which is the distributional value of data point Z is the expectation of its leave-one-out score if you add it to subsets of various size. So first I sample a size uniformly randomly and then sample a subset, a number of data points from the data distribution with that size, and compute the leave-one-out score of Z with respect to that size. So you can see it's like a very distributional and very robust version of the leave-one-out score. The good news is that it satisfies the statistical variance of the Shapley axiom, so the desirable properties they have. It's still computable with an as efficient Monte Carlo approximation method. And the definition of value this time has become more intrinsic because the value of a data point Z doesn't depend on a fixed data set. So if you take it from one data set to another data set that come from the same distribution, its value is not going to change. And in the paper, we show some applications of this. For instance, this makes data markets possible. So you can actually buy and sell data where everyone has the same valuation for the same data. And yet, because this time the definition has become distributional, there are existing knowledge, ML knowledge algorithms that we can apply to. For instance, we can show that the value this time follows Lipschitz continuity. So if you have the value of two data points, or have the value of one data point, there's another data point very close to it, you can kind of approximate the value of this one, given the value of the other one, because you have Lipschitz continuity. So thank you very much for your time and attention.
Thank you, Amirata. We have a bunch of questions. First, I'm going to call on Chirag to ask this question, and then maybe one more. Yeah, but yeah, Chirag, can you ask your question?
Hi, Amirata. Awesome talk. So just a quick question. So we were talking about how to leave samples out from a data set using data Shapley values, right? So why do you think that would work better than other ranking methods where there has been a lot of work done in identifying atypical examples from a data set, like which are hard or prototypical examples. So why do you think like data Shapley would work better in those cases?
I mean, I cannot say data Shapley will work better in every case, but I can say in general it will work better for a few reasons. The main important reason is that it's metric agnostic.
Right.
So many of the methods you're talking about are directed towards accuracy. While data Shapley can be done for any performance metrics. It can be the latency of your model. It can be the fairness of your model. It can be the performance of your model in a specific condition.
I see.
So you can find a value with respect to any metric. That's kind of the most important part of it. The second thing is that many of the methods you're talking about have some sort of an inductive bias or some sort of prior over what's bad.
Right.
So it's either noisy or out of distribution. A data Shapley is kind of directly looking at just for your metric what's good or bad. And I can easily talk about an example where you have clean in distribution data points that will just hurt your model. And if we have time, I can just go through it.
Right.
Yeah. Do we have time, Sarah, for that example or not?
Yeah, sure. If you can do it 1 minute.
So for this, you should look at my video. It's because I'm going to talk with my hands. So assume you have two classes, like two Gaussians. Class 1 Gaussian, class 2 Gaussian, and you're using a linear model. But assume class 1 has actually a very small mode here, like behind class 2. So data points in this mode are pretty clean in the distribution. That's just a distribution of class 1. But when you train a linear model, this mode is going to hurt your model every time. So you're better off just removing these
Right.
and just train a model on these two major modes. That's an example where many of the methods you're talking about wouldn't work because they wouldn't detect those data points as out of distribution because they're in the distribution and they're clean and not noisy.
I see. So it's more like a two-stage process because once we have to, we want a pre-trained model for this, right? For calculating the data Shapley's.
Oh, for data Shapley, you have to train a lot of models.
Exactly.
So that's kind of the bottleneck. You have to, for a data set of size 1,000, you have to train close to 1 million models. But I mean, we are not like OpenAI, so we did this with our own infrastructure, and it is possible because the algorithm can be ran in parallel, like extremely in parallel. Yeah.
Thank you.
Sure.
Okay, for our next question, I would like to call on Sergo Idor. Can you ask your question?
Sure. Thanks for the great talk. I was wondering the relationship between outliers and high-value data points. So are you actually effectively giving more emphasis to the outliers when you remove high-value data sets?
That's a very good point. So are you talking about this plot where when we remove high-value data points, things go bad?
This part and also your fairness results.
Oh, okay. So for the fairness results, it can be different. So here we are removing low-value data points. So you can say if you're removing things like this, things that are outliers. But as I said for the previous question, there's no specific rule for data Shapley, unlike how it works, just based on a performance. So here there are no outliers. Like the data set is super clean. It has been used widely for the past decade. It's just that it's very imbalanced towards white males. So this time what is being removed are not necessarily outliers. It's just an imbalance in kind of the subgroups you have in your data set.
I see. Okay, maybe the definition of outlier is different in this case. I was thinking outlier is like some sample that doesn't occur that often.
That's a good point. I'm not sure if we can surely say that kind of a sample would have low value. Yeah.
Okay, thank you.
Sure.
And on that note as well, I was also curious about, like high data Shapley value points, outliers, and influential points. This ICML 2017 paper by Ko and Liang about influential points. Do you have any kind of comparisons like that?
Okay, so sure. So influence functions are nothing but an approximation to the Lizzie score that we talked about in the beginning of the talk. So as you can, so Lizzie is kind of the exact version of influence functions, and as you can see, many of these applications they don't work pretty well. And there's a very good reason for it because Lizzie is just leaving one data point versus the whole data set. And let's say you have a data set of 10,000 data points. Leaving one point is not going to change anything. So by just leaving that point, like removing that point and seeing what changes, you're going to get a very noisy version of how valuable that data point actually is. So you have a data point that is super noisy, super bad. But then you combine it with 9,000 other data points, 10,000 other data points, that effect will be removed. So you can think of data Shapley value as a more robust version of influence function, but a way computationally more expensive version of it. That is looking at the data point's performance across all sizes of data, so an average behavior of it.
Cool, thanks for the clarification and explanation. Sure. So yeah, we are at time. We do have a comment from one of our attendees concerned about one of the applications in the paper about like fair gender classification based on external traits. So maybe just take a look at the Zoom Q&A tool in a bit, and maybe this is something we can discuss in our discussion later as well. Yeah, so I wanted to thank both speakers for these really interesting talks and the discussion as well. Right now we're going to go into a 5-minute break, and then we're going to go into participant-driven discussion. And at that point, everyone should be able to turn on your video and audio. And just a reminder that our next seminar that's coming up is in 2 weeks, January 21st. And we're going to have Zachary Lipton from Carnegie Mellon University who give a talk. Yeah. So yeah, thanks everyone again for coming to this very first seminar series of the year by our Trustworthy ML initiative. And we'll now do the 5-minute break and hope to see you again here after 5 minutes.